There's a lot of text in this note, so I'm going to kind of talk you through it again. I do think it's in your best interest to read it at the same time or read it first and then listen to me talk through. But do what's best for you. But here I'm going to talk you through the note. I don't intend to add anything new to the note, just sort of verbalize what's written here to help those that that style of learning helps. First of all, I'm not kidding. The normal force gets confused and mixed up a lot. I had a prof in first year that I kept in touch with at UW, and he would always talk about normal force. And when I met him after as a high school teacher, this was sort of his pet peeve, is that kids coming out of high school didn't get normal force correct all the time. Part of the issue is the normal force. It's a Newton's third law thing. We're going to talk about that. And the normal force is kind of connected to the issues we have with weight and mass. We goof up mass and weight, we interchange them, we use them improperly in everyday language all the time. So now when we need to do physics, it's important that we have mass and weight kind of figured out. We're going to circle back to this, but before I talk to it out loud, just spend like a minute. What do you think mass really is? What do you think weight really is? Can you think of examples in our everyday life where you use those words incorrectly, or someone else used one when they should be using another? The normal force, that's kind of the topic of the note. We're going to talk about Newton's second law in the vertical situation, like elevators, accelerating up and down, things like that. We'll need to understand this normal force. More generally, the normal force is a reaction to when you push on a surface. So for today's note, it's going to be a lot of like you push down on the ground reacts and pushes on you. So we'll talk about the normal force being vertical. But similarly, if you leaned a ladder against a wall, the ladder would lean against the wall would push back on the ladder. It's a wall pushing back, but could still call that a normal force. And if it's a wall pushing back, if the wall's vertical, then the normal force that the wall exerts would be horizontal. So generally, the normal force is the reaction force that a surface puts on something. It's called the normal force because normal is an old word for perpendicular, and the normal force is always perpendicular to the surface. So that's what we're trying to figure out, how a surface can react and push back on other things. If you've got the time and the equipment, well, I hope you've got the time. If you've got the equipment, we could try this as a little activity at home. I don't know what you've got in your house. I put a little picture here. If you have something, I want to call it a weigh scale, something that you would stand on or hang something from or put an item on to get mass, we could play around with that to get a feel for what the normal force really is. Now, this is the first part of our problem. Scales that you have in your house, the luggage scale, the kitchen scale, the bathroom scale, those are calibrated and they'll give you the number of kilograms or grams that the object weighs. But technically, scales aren't really reading the mass. They're figuring out the weight and then converting the weight into a kilogram number. So here, maybe you thought about it before, the difference between mass and weight. Mass is the amount of stuff. So you literally kind of get a number in kilograms for how much stuff is in an object. If you're an astronaut and you blast off and went to the moon, when you got to the moon, you would have the same mass as what you had on Earth, unless you threw up or something. Weight is a little bit different. Weight is the effect of gravity acting on the object. If you were that astronaut and went to the moon, when you got to the moon, you'd have the same mass. You just got the same amount of stuff in your body when you get there, but you'd have a lot lower weight because weight is gravity, and the gravity on the moon is weaker than the gravity on the Earth. We can manipulate weight on Earth. We can't really manipulate mass. When you put something on a weigh scale and it spits out a number in grams or kilograms or whatever, one of these scales, when you put something on a scale, spits out a number as mass, but really what it's doing is it's reading the weight and then converting the weight using that 9.8 number we learned to put that number in grams or kilograms. We can manipulate a scale and use it to learn about the normal force. Really what a scale does is it tells you the normal force acting on the object. I'm going to talk you through this. If you've got the scale, you can play with it at home. So say you got a scale. This is the one I had in my house, a kitchen scale. Pick any sort of appropriately sized object and put it on the kitchen scale. Notice that it's got a particular mass. I have my scale set in grams. That thing's reading 58 grams. It's spitting out a number, a mass number, 58 grams. But really what it's doing is it's reading, gravity's pushing this object into the ground, into the scale. The scale is reacting and pushing upward on it. Really what the scale is reading is this force. That's what I'm going to try and emphasize. But what it's doing is it's using the 9.8 number to convert it to a kilograms, or in this case, grams number. For this activity, get out a scale, get out an object and play with it. But here's what I want you to think about. What if you've got your scale with your object on it? What if you take your little finger there and you add a downward force? What if you push this object into your scale? What's that going to do to the number on the scale? Sorry. So you push down on it. What's that going to do to the number on the scale? Or, next scenario, what if you've got your object on the scale and you kind of lift up on it? Not so much that you get it completely airborne, because then the scale would read 0, but what if you just lift up a little bit? Or what if you had a helium balloon and you tied like a helium balloon to this, so the helium balloon was lifting it up? Not enough to get it airborne, but just enough to lift it up. If you do that, if you push down on it, what do you think is going to happen to the number on the scale? You haven't added any grams to it, but it's going to read a different mass. Or is it? What if you pull up on it a little bit? What is that going to do to the readout on the scale? You haven't added or taken away or added any grams, but the scale maybe reads something different, even though you haven't changed the mass. By lifting up and pushing down on it, you're going to see in a sec, you've changed the normal force, and that's what the scale is telling you. Everybody had a chance to think about it? Here's the answers, kind of at the bottom of the page. I'm going to always call it the boring case to emphasize when we're not in the boring case. But if we just have the object on the weigh scale, gravity's pulling the object down into the scale reacts and pushes upward. That's the yellow arrow here. The scale reacts and pushes upward. We're going to call that the normal force. The object didn't fly off the scale and it didn't fall through the scale. So since it's not accelerating up or down, Newton's first law, or you could say Newton's second law, the A is 0, so the F net must be 0. The F net must be 0, so that means the upward force must balance the downward force, which means that the normal force is equal to gravity. In the boring case, if there's nothing going on vertically, no extra forces, no acceleration, then the normal force is equal to gravity. In a lot of grade 10 cases, that's what we're going to have, that the normal force is equal to gravity, or the boring case. But as you'll see in this note, and you'll see a lot in grade 12, that's just a special case. The normal isn't always the same as gravity. Okay, back to our little mental scenario, or if you had a scale to try it. If you push down on the object, really what you've done is you've added a second downward force. We got gravity pulling it down, and if you push down it, I'm going to call it F applied. You've added a second downward force. The same logic as the last case, it's not flying up or down, so that means the net force has to be 0, or the total upward force has to equal the total downward force. But in this case, there's two downward forces. So the normal has to equal both of those added together. There's two things pushing down. The one normal force has to cancel them both out. If you push down on the object on your weigh scale, it's going to read a larger number. The harder you push down, the larger the number it's going to read. You're causing the normal force to have to be bigger. If you push down a little bit, the scale has to exert a bigger force to push up on you. The more you push down, the bigger normal force has to get to compensate. And the flip-flop, if you pull upward on it, not enough to get it airborne, but just upward a little bit, now the situation's a little bit different. We've added a second upward force. So the normal force is upward, and the force that your helium balloon or you've put on it is also upward. It's not flying up in the air, it's not falling down. So the up forces have to cancel the down forces. In this case, we have two upward forces, the normal and the applied force. So the normal and applied force, they team up to match gravity. Or if we flip FA to the other side, the normal force is regular gravity, minus the F applied. If you tie helium balloons to something or pull up on it a little bit, the scale is going to read a little bit of a smaller number. How much smaller depends on how hard you pull up on it. These are games you can play to trick a weigh scale. Maybe you're a little kid, like when my kids were little, they always wanted to weigh more than they really weighed. So when they were standing on the weigh scale, they would do this situation. They would like reach onto the countertop and like lift upward on the countertop, which would push them down, and add a downward F applied, which would make the normal force bigger, and the scale would read a bigger number. Or maybe, I don't know, don't want to do anything unethical, but maybe you're at like Bulk Barn and you're buying some junk food. If you lift up on the scale a little bit while it's being weighed, you can trick the scale into thinking there's less matter there than there really is. You've decreased the normal force by lifting up, so the scale is going to read a smaller number. By pushing up or pushing down at it, we haven't changed the mass, but we've changed what the normal force is. If you push down, then the normal force has to be bigger to get over gravity and the push that you're doing. Or if you lift up, then you're actually helping the normal force. The normal force is a little bit smaller when you pull up on it. Now, new scenario. Another way we can change the normal force. I don't think you should try this at home, but if you do, don't hurt yourself. Imagine you take that thing on a scale. When I typed this, I was picturing like you're using a suitcase scale. What would happen if you accelerated that thing upward? So literally just yank the suitcase harder so that it goes upward. Or what if you had your suitcase and you kind of ran up some stairs? What would happen to the number on the weigh scale, your luggage scale, if you accelerated the suitcase upward? You haven't added any mass to the suitcase, but if you yank it upward, does the scale read a bigger or smaller number? And then vice versa, what if you accelerate it down? What if you didn't let it free fall, but you kind of let it fall a little bit while you're holding on to it, or you ran down some stairs, accelerated down some stairs? What would that do to the luggage scale? I don't think anybody has one, but if you had an elevator in your house, you could try the same thing. Get a bathroom scale, put it in an elevator, see what happens when the elevator accelerates upward, see what happens when the elevator accelerates downward. Definitely don't do this at home, but what if the cable broke and the elevator went into free fall? What would the scale read? The scale is telling you the normal force. So if you can picture what a scale would do, you've already got a good grasp on what the normal force is. Here's the answer. Oops, sorry, jump. If you accelerate upward, the only way you're going to accelerate upward is if there's an unbalance. So this is Newton's first law, or you can think of it as Newton's second law. Objects accelerate when there's an unbalance, and they always accelerate in the direction of the unbalance. So if I'm telling you that the object's accelerating upward, the unbalance must be upward, which really means the upward force must be bigger than gravity. If we're talking about the normal force, when something accelerates upward, that means the normal force has to be bigger than gravity. Or if vice versa, if we're accelerating downward, the upward force must be smaller. We can't really change gravity. It's always 9.8 times the mass. So if you're accelerating upward, gravity's going to stay the same, but the normal force will get bigger to cause the acceleration. Or if we allow something to accelerate downward, gravity stays the same, but the normal force would change and get smaller. As an example, let's say we've got a 65 kilogram person and they're in an elevator. The elevator is accelerating upward at 1.5 meters per second. Per second squared. Since it's accelerating, I'm always going to start with a free body diagram. So my free body diagram is here. There's an upward force. I'm going to call that normal. I'm picturing the floor of the elevator pushing up on the person, and we can't get away from gravity. Normal is the reaction force. It's upward. If we're talking about an elevator floor, gravity is always downward. Since the question says it's accelerating upward, I know the upward force has to be bigger than the downward force. When we set up F net equals ma, a habit I'm always going to get into is I'm always going to make the bigger force the positive force. So since this one's accelerating upward, that means Fn's got to be bigger. The normal force has got to be bigger. I'm going to make the normal force the positive one. Later, if we're doing when we do a question about an object accelerating downward, I'm going to make down the positive force. So I'll flip my signs depending on the scenario. In this case, it's accelerating upward. I know the up is going to be bigger, so I'm going to make that the positive. When I set up F net equals ma, Normal force is the bigger one. I'm making that positive. Gravity's in the opposite direction, so I'm making it negative. So my F net equals ma turns into normal. Take away gravity equals m times a. And we know about gravity. Gravity is always mass times 9.8. If I wanted to get really weird, I wouldn't do it to you in grade 11, but if I made up a question about it being like in deep outer space or farther from Earth, then maybe we couldn't use Fg equals mg, but don't expect that. I wouldn't add that wrinkle to it. That's not enhancing your learning or teaching you anything if I made it weird like that. So we know F net equals ma, normal minus gravity equals ma. We know if we flip things around, normal is the ma plus the mg. We know all those numbers on the right. 65, the a was 1.5, and 65, and the g is 9.8. We can calculate the normal from that. A 65 kilogram person, if they were just standing on the elevator, if it wasn't accelerating, that's the boring case. The normal would equal gravity. Gravity's 65 times 9.8. You can do the math on that, but it's 630 something. I don't have my calculator out. If you were just a 65 kilogram person just standing on an elevator, the normal force on them would balance gravity. That's the boring case, and the normal force would be 630. A 65 kilogram person, if the elevator is accelerating up, the normal force is going to be larger. If you were on an elevator accelerating up, you would literally feel a little bit heavier than you really were. If instead of a 65 kilogram person, if we did it on like a 50 gram coffee cup, it would literally feel heavier than it is. If you're holding the 50 gram coffee cup in your hand when the elevator started to go up, it would feel a little bit heavier. You'd have to put a little bit more force on it than the regular mg to hold that coffee cup so it didn't fall. The bigger the acceleration, the bigger the difference between the normal force and the boring case gravity case. And it would be the opposite if you're accelerating down. That's all the talking I want to do for now. If you go back to that Google Slides document, there's a whole bunch of questions in there about vertical F net equals ma situations, kind of like the last one that we did. There's a weird one about Tarzan climbing a rope. If that one rattles you, maybe skip it. It's a bit of a jump, but there's some more basic ones kind of like this to like good conceptual thinking to get you started and add some math to figure out the normal force. The bottom line is the normal force is a reaction to whatever's happening in the vertical. If we add a vertical force, maybe push down on something or lift up on it, that's going to change the normal force. Or the questions I'm going to get you to do, if the object is accelerating one way or the other, this part, if an object's accelerating vertically, then the vertical forces have to change. We can't change gravity. So really what happens when something accelerates vertically, the normal force is what changes to make that acceleration happen. The normal force will get bigger to cause an upward acceleration or smaller to allow a downward acceleration. So go back to that Google Slides document, see if you can listen to some videos and be solving problems. Hopefully that'll help it click a little bit better. And then there's a check-in related to this one that you can take a look at as well. And as always, email if you have any questions.